Super fast.
You got 5 minutes. All right, we're going to go ahead and get going. Oh, wait.
Yeah, great.
We're making sure we're recording this. I'll explain why in just a moment. Thank you all for coming. First of all, this is the Stueck Lecture as part of our Academy of Civil Engineering. And just a couple words about the Academy. So the Academy of Civil Engineering was started in 1972 by Dr. Joe Senni. Unfortunately, Dr. Senni passed away this year, but he served as the chairman of this department for 20 years after being professor for some time. So he had the foresight to say we really need to honor the special people in our alumni, and he started the Academy, and since that time, picking away at it slowly by slowly, picking the absolute best of our alumni, which is really saying a lot. We've been inducted over 230 people now to the Academy of Civil Engineering. So that's the most of any academic program on campus by a good margin, I believe. And I'd like all of our Academy members in the audience today to quick stand up and be recognized. So outstanding. And the foresight is something that really kind of brings us here together today and the look at excellence. So the Academy has been around since 1972, and along the way, Neil Cornelius and Maurita Stueck sought a good idea to endow a lectureship that would bring some of the best people in the country here. So if you think about it, we want to exemplify our outstanding alumni to our students, and then we want to find people at the very highest levels globally and bring them in and exemplify what that higher level is. So always looking for that next level of excellence. And we're fortunate to have that here today. I'll give the mic over again to Chen in just a moment, also a member of our Academy, and he'll do the technical introduction. But I just really wanted to kind of get that out there that the benefit of the Stueck family really made this possible. And if you see behind me a list of the people that have been here before, Dr. Gene Corley, a really outstanding person in our field, Henry Petrosky, who's one of the premier, you switched it on me.
You can,
I'll just switch one.
you can Alt-Tab on the desktop.
Ooh, okay.
Because we're still on the computer.
Oh,
We're
I
just
got
looking
you.
at his
Okay.
slides now. You're just Alt-Tab.
That didn't work.
Can I close the browser again? I'm sorry.
Yeah, close it. That's okay. But I was just going to list up there, we've got on our site the speakers of the past, and we stay with that tradition today with Dr. Tang, who's going to give us a talk in just a few minutes. But the other thing I want to point out is we're very fortunate that Shamshir Prakash has now seen a fit to provide a second lecture series, and we're going to be kicking that off in May. So May 18th will be the first ever Shamshir Prakash lecture series, and Dr. Richard Woods, also a National Academy member from the University of Michigan, will be the inaugural speaker for that. So we're very thankful for the generosity that Shamshir has seen to put into our Academy and to maintaining this level of excellence that we expect here. And with that, I want to say thank you all for coming, and I'm going to hand it over again to Chen to do the technical introduction for our speaker today.
Thank you, Joe. It's my distinct pleasure to introduce Dr. Tang, a national member of National Academy of Engineering. He is also a foreign member of the Academy of Chinese Engineering Academy. Now, I'm not going to read everything on my list, but I mentioned a few special occasions I encountered Dr. Tang before. One is I think he was supposed to give a keynote presentation at the if I remember, it's 13 or 14 National AACE workshop on bridge engineering. He prepared all the presentation slides, but eventually I think his associate made a presentation. I want to mention is the presentation I was sitting and watched it is very, very impressive. That topic is talking about the material evolution in bridge engineering. So from very, 100 or 200 years ago, the material every different aging. So he presented a very comprehensive, inspirational talk in that national workshop. And another thing is that he was a recent speaker in U.S.-China workshop in Xi'an and also international conference on reliability in Shanghai, Chongqing University. So he has been a constant keynote speaker in civil engineering conferences and workshops in different places. Dr. Tang actually is currently chairman of the board of TY Lee International and headquartered in San Francisco. And he received his Doctor of Engineering degree from Technical University Darmstadt, Germany in 1965. He's an honorary professor of many universities, including Tsinghua, Tongji. They are best university in China. And Chongqing, Zhejiang is also best university in China. And so he has been awarded an honorary degree of Doctor of Engineering, Doctor of Literature, and Architecture. And Dr. Tang is a structural engineer. He has designed more than 100 major bridges around the world. Most of them are new construction, new design. So like people said, the sun never sets on his bridge because his bridge is distributed all around the world. Without further ado, please join me to welcome Dr. Tang.
Thank you. Well, I'm very honored to be here today. It's a beautiful area, including the rain. I'm going to talk about innovation. Now, this is a topic almost everybody's talking about nowadays. In United States, in China, in Europe, everywhere. So, but everybody may have a different opinion what innovation is. What's the difference between the life of today's elephant and that of an elephant 10,000 years ago? Always nothing. They're still roaming around the same way, right? The elephant is the same 10,000 years ago. What's the difference between our life today and those 10,000 years ago? Obviously, a lot. Now, we have created 10,000 years of civilization. That's the difference. We humans have the capability and courage to innovate. Innovation brings improvements. So we live better and better. So the advancement of civilization results from the accumulation of innovations. The more we innovate, the better life we have. Without innovation, we probably still live in caves today. So maybe even worse than the elephant. What is civilization? Civilization, according to Webster, is modern comforts and conveniences made possible by science and technology. How do we make it possible? Through innovations. Simple. So what is innovation? How do we innovate? And who can innovate? These are the big questions. Innovation starts with the I. So we'll have many I's to talk about. So innovation includes invention, improvements, and integrations. The three I's of innovation. Inventions, everybody knows that a new idea, right? Creation of a new idea. Make something impossible possible. So because of innovation, that impossible become possible. So like light bulb. Light bulb was not there before it was invented, but once you have a light bulb, the life changed. We have today WeChat, Facebook, Twitter. They were not there before. So when I went to school, we never knew something like that. But they are recent innovations. They changed the way we live. So the steel production methods, for instance, the Bessemer process and the Siemens-Martin process are definitely great inventions, because without production of steel, today we're probably still living in stone houses. So there have been in between, a lot of improvements on this steel we have. So, for instance, steel strength. When I went to school, we were talking about 20 megapascal or something like that. Now we're talking about 100 KSI. So the improvement is to modify and make it better. That's improvement. So remember the old days, wow, they're all young people here. So in the old days, when you want to listen to music, you have to go home. Because you cannot carry the radio around. And then the Walkman came. So we can carry the Walkman. Some people carry a big one and go all around the park, right? But the Walkman is an improvement of the old radio. The iPod is another step improvement. And then today, your iPhone or your smartphone has all the music you want, anytime. So these are improvements. What's integration? It's to combine existing ideas to create something new. So that's what Steve Jobs has said, creativity is connecting things. And look at the iPhone. The first iPhone came out, there's nothing new in the iPhone. They just combine everything together. So that becomes the iPhone, something new. And that's incorporation. So for bridges, I'm a bridge person, right? There's a lot of examples. For instance, reinforced concrete. Putting steel in concrete to give it a capacity to take tension and bending moment. So otherwise, we would not be able to build longer beams or bridges. Put pre-stressing into concrete, improve it further. We talk about arches. Original arch was built with 2 horizontal force because it would have a horizontal force to the ground. But now we put a tie, then we don't need the horizontal force. So that's an improvement. Just like, for instance, top one's the Hoover Dam, we put the horizontal force to the abutments, to the ground. And the bottom one is a tie arch, which we tie them together so we don't have any force going into the foundation. For segmental bridges, it's an improvement because without segmental bridge construction, we would not be able to build any long span concrete bridges. Precast construction, again, is an improvement. It simplifies construction and improves quality. And we can also nowadays put tendon outside of the concrete, which we call external tendons. This makes the construction much faster, but also it improves under earthquake. And cable stay bridges, we use cable to pick up the loading from the girder so we can build very long spans. For self-anchored suspension bridge, a similar like arch, we can put the horizontal force back to the girder. And then the autotropic deck make the bridge much lighter. And aerodynamic cross sections. These are all improvements. So the 3 I's of innovation. But then what's the purpose of the innovation? Why do we innovate? It must have a meaning. So the purpose of innovation is to increase value, to create value, to increase value. If it's not better, it's not innovation. If you're better off, it's good. If you're worse off, why do you innovate? So increased value is very important in innovation. Therefore, we have the 4th I, increased value. Without increased value, it's the alternative, or actually a worse alternative. So now I have the 4 I's of innovation. To increase value is the purpose of the innovation. For example, what's the value of a bridge A bridge, we all say, it must be safe, functional, economical, and good looking. Otherwise, it's not a bridge. If you build a bridge without aesthetic, it's a garbage. So a bridge must be all this. So therefore, a bridge has the value of safety, the value of functionality, the value of economy, and the value of aesthetics. Each has its own value. And the total value of these four, summing up, is the value of the bridge. Yeah. Actually, this is applicable to anything, not only bridges. Like you're buying a car, a house, or a pair of shoes. You have exactly the same requirements. For instance, let's say we buy a car. We want a car to be safe, definitely, right? It has to be functional, definitely. And it has to be economical, unless you have too much money, right? And it has to be good looking. Obviously, each of them has a value. But different people would have put different value on different items. Because, for instance, somebody may want to have an absolutely safe car. It doesn't care about aesthetics. So, or somebody like a good-looking car, right? For instance, if you can improve the cash mileage of a car, that's increased value. That's economy. We all know that the better-looking car always sells better, and that's aesthetics. Because it increases the value of the beauty. So this is increased value. Obviously, innovation incurs additional risks, and it definitely requires more work. So why would anyone want to innovate? Yes, why would anyone want to innovate to spend more time and take more risks? So therefore, innovation does not happen by itself. Innovation requires encouragement. That means incentive. You have to have incentive for somebody, otherwise nobody is going to innovate. The simple question, what's in it for me? So therefore, we have the fifth I, the incentive. So these are the 5 I's of innovation. The first 3, inventions, improvements, integrations, is the definition. Increased value is a requirement. It has to increase value, otherwise no innovation. The incentive is inducement to innovate. We must innovate, very simple. But how? How do we innovate? The how is a process. Let's make it very simple. I guess a lot of people talk about innovation, and everybody have a different way of telling you how to innovate. I just make it very simple. The innovation, how to innovate, is to answer these 3 questions: why not, and what if. The 3 questions to the role of innovation. Why? To challenge the status quo. Now, if you do not ask why, you will be doing the same thing year after year. What your grandfather do, you're still doing that. That means you never change, and they will never innovate. So if we were still living in caves, we'd still be living in caves if nobody asks why. So whatever your grandfather did does not have to be right. They may have done it many centuries ago. Whatever your professor told you, I'm sorry, your professor here, but it might be outdated. I mean, or it could be wrong too. I mean, everybody can be wrong. You know? And whatever you had to read from books could be wrong also. So therefore, we ask why. And the second question, why not, is to introduce your new ideas. You know why it happened that way. Why do you have to do that? Now you may have a better idea. So you change it. So can we have a better alternative? That's the question, why not? We need to say that, we should say that thinking out of the box. So if you do not ask why, you're always in the box. When you ask why and why not, now you are now outside the box. So that means you are not following exactly what other people have done. Once you're outside the box, you're no more in your comfort zone, because now you're in a strange area. Therefore, you must ask at the third group of questions, what if? What if is to keep you from straying outside of the possible? Now you must study and investigate. It's now your idea. You are responsible for it. So therefore, you have to be careful that what you say you want to do is correct. And you must make everything right. We must ask what if to make sure you introduce is acceptable. Here I give you an example. Well, a bridge is too small. So let's talk about big things. Right? What's big things? Economic. You remember the subprime crisis? I guess most people here would have lived through the subprime crisis, where a lot of people lost their home. How did it happen? People were very innovative. So they asked why and why not, very innovatively, but forgot to ask what if. Now, if you look at the house price, this is the curve of the house price. And that's the point where we have the crash. Now let's go back to 2000 and try to predict. Let's go back, turn back the time. In the year 2000, we're standing right at that point. So how do we predict the future? So you can go up, go horizontal, or go down. If we had used the data from the last 30 years, that would be what happened. Now, some people might have asked, why 30 years? Why not 6 years? Or actually, in reality, what I understood was that they didn't even use 6 years data, they used only 2 years or 1 year data. But anyway, let's talk like 6 years. And that's the data from that 6 years. If we project everything from these 6 years, and that's what we get. And that's what happened. And that's how they priced the index. So that's exactly what went up too fast or has to go down, right? And we have to crash there. So, because nobody asked what if, why only 6? Why we have 30 years of data? Why don't we use, say, 30 years data? So, if you ask what if to keep you straying from the possible, because you are may go to the impossible. House price cannot always go up. We must ask what if. So you must make sure everything's okay. Yeah? So when we go back, we have the definition, requirement, and inducement for innovations. And we also talk about how we innovate, the procedure, the 5 I and 3 Ws. But not everybody can be an innovator And we don't want everybody to innovate because otherwise the society would be messy. Therefore, it's good that not everybody can be an innovator just because he wanted to. An innovator must have capability, courage, and chance. So capability is equal to knowledge. If you do not have enough knowledge, you cannot even ask why. Or even if you ask why, you would not have an answer because you don't know enough. So capability is very important. So for us to have an innovative society, we have to have good education. That's your responsibility. Courage. If you do not have the courage, you will not ask why not, because you are in a very unknown territory. So to be innovative, you must have the courage to introduce your own idea and stick with it. So when you innovate, you're doing something nobody has done before. It's outside of your comfort zone. So you need courage to carry on. Here I have an interesting example about courage. A topic many engineers are talking about today. Sustainability. I think everybody has been in that area. The world has to be sustainable. So we know that this planet cannot support us if we keep on living the way we living today. So we are working hard to design green buildings, green transportations, and everything so that we have less carbon emission and we use less material, etc., etc. What is sustainability? Sustainability was defined by United Nations as sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Now, how much we know about the future generation? Do we know them? In 1914, people could never imagine how we live today. It's only 100 years. The Earth has been 10 billion years old, so this only short 100 years, they would not even dream of how we live. But today, it's equally impossible for us to know how people live 100 years later. That's very obvious. So that when we talk about sustainability, there are two unknowns here, quantity and quality. So we have to know in the future, for the future generation, we have to know how many are they, how many people we have, and how much so each have. There's a standard, the living standard. So the total quantity to be provided to our future generation is equal to N times Q. It's a very simple equation. Always this is a simplified equation. The Q is the average. So we can also say N is the future population and Q is the living standard. So if we can assure that we can provide W for future generation, the Earth is sustainable. If we cannot, then it's not sustainable. It's a very simple idea. So let's look at N times Q. When engineers talk about sustainability, they only talk about Q. They never talk about N. So how could we control waste, limit carbon emission, reduce energy consumption? That's all engineers do. If we work very hard, how much could we reduce? 20% or 50%? If you invent something, you can reduce 50% of energy, everybody, you'll be a billionaire immediately. So it's not easy. when we talk about why not, what if, we asked why. So we found out Q is a problem. So therefore we work on the Q. If we ask why not, so also we are working only to reduce the Q, so we are, because we're engineers, we have not asked the what if, why. So if you look back to this equation, there's only two terms, N and Q. What's N? What if N explodes? If we Q can reduce 50%, if N increase 100%, we have done nothing. So N is very important. And what if N increase faster than the Q, we can reduce. So that's our question. How about N? N is that how many are they in the future generation? We don't know, but we can make some assumptions. Because if it's very obvious, the more people we have, the more quantity we must provide. Because W equal to N times Q. If N keep increasing, W must be increased. The problem is N is a variable. We don't know. This is a very scary plot here. The world population in the last 20,000 years. So we are at that point. Let's forget about this 20,000 years. We only look about the last 2,000 years. But still pretty scary. So if we take these 2,000 years and replot it, it looks like this. And we are, the last very correct numbers, in 2014, we have 7.15 billion people on this earth. But how do we go further? If you look at this curve, you extend the curve, you know what could happen. So if we look at numbers, this is how it looks like. So in 100 years, from 1914 to 2014, world population increased from 1.7 billion to 7.15 billion. 100 years. That's a 320% increase. We were talking about Q of 30%, 50%. Here we have 320% increase already happening. So what if? If you look back to the population growth rate, it doesn't look that bad. Mostly only 0.5%, something like that. But you're all engineers, so you know the numbers very well. If we projected a 0.5% increase, annual increase into the future, in 500 years, we will have 86 billion people. That is 12 times today's population. 0.5%. If you talk to a politician, 0.5%, they didn't even talk about it. So the number is very simple. 1.005 to the power of 500 is 12.10684. As an engineer, this number is so obvious. Try to imagine, take any city in the US today and multiply by 12, even roller. So it's a very, very solid problem. So we do not do something very soon. One day there would be standing room only. Think about 12 times. In New York City, if you're 12 times the population, you have to swim on the East River. So standing room only look like that. So going back to the 0.5%, let's look at what reality is. This is 2014 statistics, because that is more correct. In 2014, United States had 314 million people, 4% of the world, and we're increasing 0.74% per year. China is increasing 0.49%, and India 1.46%. Now the total is 1.2% increase per year. What does that mean? At 1.2% growth rate, 500 years later, we would have 2,783 billion people on Earth, 388 times today's population. 388 times today's population. So 500 years is a short period of time for the Earth history. So there are such simple numbers. Why don't our politicians talk about it? Have you ever heard about population control? This, to my opinion, is a lack of courage. We know the problem, we know the solution, but well, people say today that, for instance, Japan or in the United States, well, not in Japan and Germany, or even in France, population is decreasing, but only area. But Germany and Japan is encouraging people to have more children now. So is China. So therefore, every country is worried about decreasing in population. What end up is that there are a lot of people do not worry about anything, then they have a lot of children and they have a lot of population, that they have a lot of increases. So obviously we need more than just population control to solve the problem. But population is the biggest problem, and nobody is talking about that. So coming back, we look at this equation. We're trying very hard to work on Q, 30%, 50%. If population can increase by multiple of 100%, our effort is meaningless. So without solving the population problem, there will be no feasible solution for sustainability. Unfortunately, the correct answer is politically incorrect. Our politician has no courage. And to my opinion, the only country which talk about population control is China. When I went to school, China has 450 million people. When I started working, China had about 1.1 billion people. Because Chinese, the numbers are very complicated. So in that time period, about 30-some years, the Chinese population increased over 200%. If China had not stopped that, today China would have 5 billion people. And there's no way China can support that. So they start to have birth control. Rightly or wrongly, that's the only way China can go to make it work. Otherwise, you will have all the Chinese over all the world today. So, courage is important. If you want to innovate, you must have courage. Chance. Obviously, if you do not have a chance to apply your idea, why will you go to innovate? So, to be innovative, one must have the opportunity to apply his idea. There are two types of opportunity. One is opportunity offered by the society, that you go to do something already existing, improvement and so. And another one is the opportunity you create yourself. If you don't get a chance, you create your own chance. So for example, the smartphone. Now everybody has a smartphone, right? Before the smartphone was introduced on the market, nobody had talked about smartphone. So the smartphone actually created its own market. And that means it creates its own chance. The world is changing very fast. This change gives us a lot of opportunity to innovate because there's a lot of new things coming too. Just like when you talk about bridges, in the old days we used stones. Now steel comes on, we can use steel. Wire comes on, we can build suspension bridges. So the world changing, and because of this change, we have opportunities. So something unthinkable in the past may become a hottest fashion today. Just think about it. A lot of things didn't exist when I was a student. So, and whatever exists when I was a student, you don't see it anymore. Just like the big radios, the slide rules. Right? I spent a lot of time to learn the slide rule, and then the younger people don't even know what it is. No. Now I'll give you one example. Now this one is absolutely unimaginable, to my opinion. I'm an old man, right? But I don't know what you think. But it's really extraordinary. The ripped jeans. Now when I was young, no one dare wear a jean like that. My father would kick me out the door. And this one, absolutely no way. But if you look at this, there's prices. Each hole costs more than the jean itself. Why would the lady buy the holes? So that is really, you have to sit down and think about that. It's really a big innovation. So this one in import from Korea, they call it beggar style. A beggar style. Why does anyone want to look like beggar? So it's really something. So therefore, this example shows you that if you are innovative enough, there are unlimited chances. You have to sell ripping and holes for a profit. If you have a patent on that, you're definitely a billionaire. So why is this an innovation? What value does it create? So first, the jean seller, he means profit. Profit is money, so he definitely that's a value for them. If you have money, it's value. Second, you do not have to throw away your old jeans because your old jeans is bigger. You have a hole, you make it bigger. So therefore, it's a lot of value there. He said, so people have been wearing jeans for over a century. There's a long history. There's still room for innovation. So to summarize, so innovation has 3 I's, 3 W, and 3 C's. The 3 I's, the 5 I's is invention, improvements, integrations, increased value, and incentive. And the 3 W is why not, what if. And the 3 C is capability, courage, and chance. The 5 I's is the definition, 3 W is a procedure, and 3 C's is the prerequisites. Are there a lot of Chinese students here? In China, they use numbers. They use a number to tell a lot of things. For instance, if somebody sends you a number 520, you know what it means? It means I love you. And the Chinese student will know that. So 533 in the Chinese means I'm going to think about it. So 533, remember that. Another example. A bridge engineer certainly have to talk about bridges. So the new eastern span of the San Francisco-Oakland Bay Bridge. This is a new bridge, $6 billion. So up to now, all suspension bridges in seismic area have portal towers. Now San Francisco has the highest seismic area in United States. So what is portal tower? So portal tower is this, and the single pole towers. Now, up to now, we all have portal towers. But for this bridge, the owner has organized a committee with 34 specialists or experts all around the world. And they said they want a single pole tower. They know that it doesn't work according to the specification at that time, but they want a single pole tower. So what did we do? Because the prevailing provisions would not allow that. We asked why. This is the portal tower, 2 vertical columns, and with portal you have to have cross beams. This is the portal tower. So how does it behave? It will look like this, Carquinez Bridge. So why? During an earthquake, plastic hinge can form in the cross beams and leave the vertical column intact, so it can still carry the vertical load. These are where the plastic hinge forms in the earthquake when it moves. So because the function of the columns is to carry vertical load. Now, if a single pole tower, if it starts to move, the hinge form at the bottom, it becomes unstable. So therefore, that's why the specification would not allow that. This is why. So, but we have to try to make it work because the boss says so, right? So the Bay Bridge is a very wide bridge. It's a 2 5-lane bridge. There would be a traditional tower, portal tower, but that's what the owner prefers. So instead, we think about why not do something different? If we put the 2 columns closer together, it's still a portal, right? It's just narrower. And then we can also put more crossbeam to that. And finally, that's what we get. That's how the bridge looks like. And you can see that the bridge, actually, the column is 4 vertical columns combined together, but it looks like a single column. So the architect is happy, the owner is happy, everybody's happy. So, and this is what we have done to make something impossible possible. Because if the specification said you cannot do that, that means impossible. Now we make it possible. The bridge is finished. So if you go to San Francisco, make sure to look at it. It's a very beautiful bridge. That's innovation. That's how the bridge looks like. Actually, the old bridge has been dismantled now. And that's how it looks. So innovation is a lot of fun. A lot of fun though, yeah. The ultimate goal of civilization is to make our life more enjoyable. That's the only reason why we have civilization. So therefore, how can a life be enjoyable if there's no fun? That's my opinion. I don't know what you think. So I'm going to show you how much fun we can have in designing bridges. Let's take one example, arch bridges. There are all different types of arch bridges. These are field designed by us. And these are all arch bridges. Look at that. They're always vertical. And we just talked about Hoover Dam Bridge this morning, and this is also vertical. And the Roman arches are vertical, and the Chinese arches are all vertical. Right? Why are they all vertical? Because almost all loads on the arch is vertical. So we put a vertical arch to support the vertical load. It's very, very reasonable, makes sense. Right? But they don't have to. So then we asked why we cannot have inclined arches. So we're vertical, why don't we do this, right? So here I show you a few arch bridges I designed, which is inclined, not vertical. Well, let's look at the Guangdong Bridge. This the Guangdong Bridge in Taiwan. That's a design done by Professor T.Y. Lin, my predecessor. He also have vertical arches. It's a nice looking bridge, but it's also vertical. So the vertical ribs, if we push it inwards, so they will look like the Bar Bridge I just showed you. And this is what we call the basket handle type bridge. It works, it looks great. And that's Chongqing, as you see. And now we push it inwards. Could we push it outward? Sure, why not? So we do this. Is this what we get? That's the Dagu Bridge in Tianjin, in China. The two arches are sloping outside. When you drive on the bridge, it's very, very open, very nice. So, and the pedestrian walkway, and this is the bridge when you're looking at in the daytime from the river, and this at the nighttime is a beautiful bridge. So, so when we look at this bridge, we put the two arches outside. Right? Why couldn't we put arch in the middle? So we push the arch to the middle, and that's what we do. And that's what we get. The Huailou Bridge in China, then we push the arch in the middle. And this is how the bridge looks like. And this is a construction drawing, picture. And okay, let's do another twist, right? We like this. Why can't we do this? So we can twist around 90 degrees. That's what we get. Like this and like this. Right? So this is the Sanhou Bridge in China. It's a very interesting bridge. They call the butterfly on the river. As a matter of fact, when this bridge was open to traffic the same day, the real estate in the area increased 17%. This becomes a very well-light area. So different views of the bridge. From here, can we do something? Let's put the arch together. So twist them together, and that's our next bridge, called Taijiang Bridge in Fujian. That's how the bridge looks like. And that's the completed bridge. The bridge, the arch tower is actually a very simple calculation, a simple system for structural engineer, the arch with the tie is very stable. You have only two vertical members to support it. And because all cable come to the center, you have absolutely no horizontal force. So that's a very stable structure. And that's how it looks like day and night. Can we do something more? Okay, let's turn it 90 degrees. Actually, 180 degrees. That's the complete different look. We just turn it upside down. So there are many ways to build an arch. Not always have the vertical. For 2,000 years, we always vertical. Now we have different ones. This is the Dongying Bridge. We can do an arch like that. Or pick it horizontally. And that's how it looks like. And this is one of Professor T.Y. Lin's bridge, a horizontal curve, cable stay bridge. There are infinite possibilities. So let's summarize the 5I, 3W, and 3Cs. Try your innovative idea at home and have fun. Thank you.
We have some time for questions from the audience. Any questions?
If you ask questions, you have to be louder because my hearing is.
Yeah.
For your inspiration, do you just sit down and sketch a different arch and just sit down with a cocktail napkin and draw things out, or how do you come up with some of those?
That's very simple. I say that you have to have the capability first.
Oh, well, I'm sorry.
Well, each of these arch bridges have a completely different behavior. So the design is completely different.
Yes, go ahead.
All those different variations of the arch are ingenious and very interesting to look at. Do any of them not work because of things like vibration from wind and other dynamic conditions?
I'm sorry, I didn't hear.
He's asking whether any of this design will have an issue with dynamic loading on the wing or other type of.
No, we do not. We don't have any problem. Actually, for instance, the Dagu Bridge in Tianjin is in a high seismic area. The bridge, when you take out the foundation, the bridge itself is a completely stable. So we have put it in 4 vertical columns. You can run around any movement, the bridge will be still stable. So actually it's the highest seismic area in China. Yeah.
Any others? Yes.
With the innovative structures, is there a close collaboration with the designer and the contractor? Because I imagine this takes some innovation construction too.
Do you mean the aesthetic or the?
He's talking about with your innovative design, the construction process may also unique. So how do you collaborate with design and construction side now?
Actually, we also design the construction.
Yeah, they are full set.
Actually, as a bridge engineer, you have to be able to see the bridge come from beginning to the end. If you do not know construction, you cannot design a good bridge. Because you cannot design a bridge which cannot be built. Right? So it's important to know. And then people ask me about aesthetics. I think engineers should know aesthetics too. And that's why actually they give me an honor degree on architecture. You know, in all my career, the engineer and architect always fight each other. They always like that. But now I tell them I'm also an architect, so no argument. Yes, sir.
Yes.
Doctor, what do you think from 1860 to 1950s, we were doing bridges pretty stable, a couple suspension bridges. Then from the 60s on, we took off with the cable stayed and just went crazy. What changed so much in our dynamics, or was it the fact that they finally let the engineer and the architect loose and do his own thing?
I can do with that.
Well, he said before 1960 and after 1960,
Yeah.
there's a significant change in the way we build like a suspension bridge along the bridge. What kind of dynamics changed that?
Mainly the cable. Actually, before 1960, we have suspension bridge, we have girder bridge, and we have arch bridge. The only difference, then, in 1955, we built the first cable stay bridge. This is by the Germans in Sweden. So after that, the cable stay bridge become very popular. People like the shape, and also it's very economical for the medium range, maybe 200 meter, 300 meter range. So that's why very rapidly there are a lot of cable stay bridges being built. But otherwise, not much different.
Any other questions? Now I'm going to summarize his presentation and Dr. Tang. So what also in 3 words, IWC. I mean inspirational. W is very wise, in the wide knowledge, you can see that. C is very, very creative. Okay, with that, thank you very much for your participation. Oh, yeah. Yes.
We're going to thank Dr. Tang, and then we've got some award presentations for some students from last night. So first, thank you, Dr. Tang.